This lecture is about correlation, which is a measure of a certain kind of association between two numerical variables. We need such measures in order to make predictions. To predict the value of a variable, something we very commonly do is we identify some other variables that are associated with what we are trying to predict. These other variables are called attributes. For example, if you are trying to predict the outcome of a certain patient undergoing a medical treatment, then you might look at their medical history, their age, their gender, and so on. These are attributes that will be associated with their outcome. And if you can measure these, and crucially, if you can describe the relation between these attributes and what you're trying to predict, then for the new patient, you can measure all those attributes and use your description to make a prediction. This relies on your being able to describe as precisely as possible the relation between the attributes and what you're trying to predict. And so we're going to start out by trying to describe the relation between two numerical variables. As always, it's good to start with visualization, and if you are trying to describe the relation between two numerical variables, you'll recall that what you do is you draw a scatter plot. In the scatter plot, you might see a trend. What does trend mean? It's just some general upward or downward movement. So as the values of one variable get larger, then typically the other one do as well. If that is the case, then your scatter diagram will in general be sloping upwards, and we'll say it has a positive association, or it shows a positive association. If it's generally sloping downwards, we'll say it shows a negative association. Now, not all scatter diagrams have to show a clear positive or negative association. Some might be wavy. They might show some kind of pattern and not necessarily always go up or always go down. A pattern is any discernible shape in the scatter diagram. The pattern may be linear or it may be nonlinear. You've seen many scatter plots and you know that the shapes can be quite different. So we'll start out first by looking at shapes of scatter plots, and then we will try to quantify some of what we see. Visualize, then quantify. That's the motto of our course. Our first data set is one of the data sets that started this whole way of making predictions. You remember that Francis Galton was trying to predict the attributes of children based on those of their parents, and one of the features he was looking at was height. And so here is a data set that you've seen before. There are 934 adult children, and here you have their heights in inches. In the first column, you have a kind of average of the heights of their parents. If we draw a scatter diagram, let me remind you of the call. So table.scatter. If you provide just one column label, then you will get the scatter diagram of every other variable against this one. Well, we only have one other one. So we will get a scatter diagram that has this variable on the horizontal axis and the other one on the vertical. What can you see by looking at that scatter? Do you see a trend? Yes, you do. You see a general upwards trend. I think you can also see that it's generally linear. This scatter diagram isn't waving like that. It tends to be following a straight line, though of course it's not the points are not exactly on the line, they're somewhat off. This is a typical linear relationship, we'll be talking much more about exactly which line and how to use that line to make predictions. For now, let's just note that the trend is positive. There's positive association, and this roughly looks linear. Not all scatter plots look linear. Let's take a data set that we haven't yet seen. This is a data set on hybrid cars. The table hybrid contains the data on 153 models of hybrid cars that were built, I think, between the years 1997 and 2013. Each row corresponds to a model of car, not a car, but a model. The first column contains the name of the model. The second is the year of manufacture, or the year that car was released. The third column is the manufacturer's suggested retail price. This is a number in 2013 dollars. This is how much the car costs. The column after that is a measure of acceleration. The bigger this number is, the faster this car accelerates. So from a standing start, getting up to, say, freeway speeds, is faster if this number is larger. The column after that is a measure of fuel economy, miles per gallon, MPG. More miles per gallon means the car is more economical. For each gallon, it goes more miles. Now, this was very significant with hybrid cars. The final column represents the class of the car. Some cars are called compact, others are called SUVs, and so on and so forth. What we're going to look at is what people were paying for. These prices, what are they associated with? And the first thing we're going to do is we're going to look at a scatter diagram of price on the vertical axis and fuel economy on the horizontal. The first column label is X, the horizontal axis, and the second one is the vertical. Let's take a look at what this scatter diagram shows. Linear or nonlinear? What do you think? Nonlinear, that's right. There's a curve here, clearly. But more interestingly, positive association or negative? Pretty clearly negative. What does that mean? The more the miles per gallon, the less the price. Really? The more economical the car in terms of fuel, that is, the more miles it can go on a gallon of gas, the less people were paying for it on average. That's very strange. You think that if you're buying a hybrid car, then you're going for fuel economy. But among hybrid cars, clearly not. So then, let's take a look at the price versus acceleration. So now we're going to have acceleration on the horizontal axis and price on the vertical. And lo and behold, positive and sort of linear. So the higher the acceleration, the faster the car can get up to high speeds, the more people are willing to pay for it. So, hybrid or not, what you're seeing is an association between acceleration, positive association between acceleration and price. The cars that accelerate faster also command typically higher prices. Now, we're not concluding causation. There could be some other reason for the higher prices. Maybe the cars that accelerate fast also have some other wonderful feature for which people are willing to pay. But there is clearly a positive association between acceleration and price, whereas there is a negative association between fuel economy and price. That's quite interesting. Remember that this scatter diagram represents about 150 different models. Sometimes when you reduce your data set to a more homogeneous group of individuals, you see slightly different patterns. What we're going to do next is we are going to restrict ourselves to just the sport utility vehicles, the SUVs. So we will create a new table called SUV by applying the where method to the hybrid table. Hybrid.where class, this is a column label, is SUV. The first thing we're going to do is see how many such models there were. There were 39 such models. What we're now going to do is, for those 39 models, we are going to draw a scatter diagram of price versus fuel economy. As before, we see a negative association. The higher the miles per gallon, the greater the economy, in general, the less the price that is being suggested by the retailers. We saw that same negative association in the entire population of models. However, this diagram has a somewhat linear appearance compared to the original diagram that was sort of clearly non-linear. You can't see in 39 points, you can't necessarily see things very clearly, but it is worth noting that when you restrict to homogeneous groups within a population, scatter plots can look rather different. There's something else that's worth noticing. When you look at a scatter plot and you say, oh, this one's nonlinear, there's negative association and so on, how hard do you have to look at the numbers on the two axes? I'm going to say not very hard at all. There is a general shape that you can see, and the fact that the numbers here go from 20 to 70 makes little difference. They could have gone from 2 to 7 and you would have seen the same shape if you drew it on the appropriate scale. And this observation, that you can look at shape and you can look at trend regardless of exactly what's on the two axes, that is, regardless of exactly what the units of measurement are on the two axes, is a signal that perhaps all that matters are standard units. Do you remember standard units? Yeah, where the average is called 0 and the SD is called 1. Basically, you stand at the average and you measure in units of SDs. We are going to look at these same scatter diagrams with the variables drawn in standard units. Here is the definition of the standard units function, and it takes an array X and it converts it to standard units. So it returns the entire array converted to standard units. To convert to standard units, you subtract off the average and you divide by the standard deviation. What we have done in this cell is we have created a table with the fuel economy, miles per gallon, and the retail price, but both in standard units. We have applied the standard units function to the original columns of economy and price. And then we've drawn a scatter diagram which looks pretty much exactly the same as the previous scatter diagram that we had drawn. The scale is a little different, but it's discernibly the same scatter, except now you know what the average of the price, what the average of the economy was, what the average of the price was, and how big a standard deviation was on either side. We've drawn it on what is called the standard unit scale. And you can still see the trend and you can still see the pattern. What this is telling us is that we might be able to measure the association, or at least measure some kinds of association, based on standard units. That's what we're going to do.